Hello and welcome to this technical tutorial video. I'm going to have a look at PoE today. I've got a bunch of PoE devices here which we're going to have a look at. Got some switches here that do PoE. This is a TP link. We've got a Netgear GS308P. We've got a Netgear FS108P. And we've got a Cisco Meraki MS switch, which all provide power over Ethernet. We've also got a couple of injectors here. We've got a 48 volt output injector, and we've also got this 18 volt output injector. And we're just going to run a variety of tests on these devices and just see what we can learn about PoE and how it works. So PoE is a technology to provide power over Ethernet, and I've also got this power over Ethernet tester. So let's have a little play around with this tester, which is quite easy to use. We just plug it in to the device. Let's try this first. We've got this 48 volt injector. So the idea of this is we can plug it to a non-PoE switch, and it provides what's called passive PoE. Passive PoE, it means that it doesn't carry out any negotiation. It just pumps out 48 volts or thereabouts on a couple of the copper pairs. So I'll just show you what I mean. Okay, so when we turn that on, we can see that the Midspan light turns on. Okay, let's try the same thing on this 18 volt injector. See what happens. Okay, nothing. Okay, the reason for that is because 18 volts is not the standard. It's not the PoE standard. So this tester is testing to make sure it meets the correct standard for power over Ethernet. So it's expecting to detect 48 volts or 50 volts ish on the correct copper pairs. So there's a couple of differences here. I'll just show you the difference here on these switches. So if I connect this same tester to the Meraki switch, so this is the Meraki. Let's just do that again. I just wanted to do that again to show you that there's sometimes a delay. See that? Whereas when you do that with an injector, you'll never get that same delay. It's straight away. See? Every time it immediately, do it the other way around. Every time it immediately lights up. Bang. Bang. But with a switch, there's a very, very slight delay sometimes because it carries out a little layer 1 negotiation, which I'll explain how that works. And you get this on the, let's try this on this switch. Okay, slightly longer delay that time. Okay, so that one seems a bit slower than the others. Let's try this one. Again, a bit slower. Again, a bit slower. So the Netgear seems a bit slower. That one's not quite as slow. Little delay there with the TP link. The delay doesn't really matter. It's just the way the PSE, this is called the PSE because it's the power supplying device. It doesn't, you know, the delay is not hugely important. It's just interesting to see how these different devices work. Because they're all essentially doing the same thing. They're providing power to a power over Ethernet device. Let's have a look at how that magic happens. Okay, so this is a cable I've made where I've just taken all the positive parts of an Ethernet cable. So every copper wire on an Ethernet cable has a purpose. There are eight in all. So you can see here we've got our 8 colours in an Ethernet cable. and I've just split them out into positive and negative so we can read. So there's two types of PoE. There's mode A and mode B, or also known as passive or active, and sometimes midspan, which is what this calls it, midspan or endspan. So the reason it's called midspan when you're using an injector is because the injector sits in the middle of a switch and a device, I guess. That's what's called midspan. Okay, so using this specially made cable, I'm just going to test the voltage using a multimeter here, okay? So let's see what voltage we get when we test our PoE injector here. Okay, just a word of warning, I am toying with electric and voltage and current, and I don't recommend that anyone does this. I'm messing around and I'm not a qualified electrician, and I have created sparks and broken things, okay? So this is just for entertainment purposes only. Don't go ahead and do this, please, thank you. So let's just test the voltage we get from this cable. We've got this running out of a power over Ethernet injector, and we are getting 47.9 volts. Okay, so that's meeting the standard for power over Ethernet, and as you can see, it's a steady voltage, just no movement here. Oh, 48 volts. Okay, 48 volts, just nice steady voltage flowing through this cable from our injector. Okay, and let's have a look at the same for this one here. This is the 18 volt one. Okay, okay, so let's connect this to these parts here, and there we go, 18.01, 18.02, 18 volts coming out from there. Okay, so we can see that our multimeter can easily read what's happening with these devices, but we don't know what wires are being used in here. Okay, but this is just an easier cable to use for demonstration purposes. Let's just see what's happening on our PoE devices, okay, because these should be supplying the same voltage to an endpoint. Okay, but what's happening here is quite interesting. You can see on this TP-Link one, we've got voltage flying around and it's fluctuating. It's giving us 2 volts, 3 volts, 4 volts. It seems to go through this cycle of providing this different voltage. But it never goes above that, and that's quite important. And we're going to learn why. Let's have a look at the netgear. Similar kind of thing happening here. You can see that it's very low. Yeah, you can see there's a decimal point there. So it's 0.7 volts, 0.9 volts, and then 1.3 volts. Okay. Let's have a look at this one. Probably the same, because netgear probably follow the same kind of pattern. Okay, it's slightly different. We've got millivolts. If you notice the reading on the multimeter has changed. This is all in millivolts. We've got 35 millivolts, 19, 18, sort of flickering around. Let's have a look at what the Meraki does. Okay, again, millivolts, 10 millivolts, 11 millivolts, 14 millivolts, 25, 112 millivolts. Now, was it just flicked up to volts on one of those? Very briefly, but these are very low amounts. It's never going over 1, 2, maybe 3 volts, you know, all of these switches. I think the TP-Link one gave us the maximum, which was about 3 something. Yeah, 3 volts, but it's never going over 4. Okay, 4 volts. A very quick 4. In fact, that was 0.4, was it? No, it was 4. 4.14. Okay, so this is we can see that already there's a difference between all of these devices. They're all doing something slightly differently. But let's have a look and see the behavior of a device which is powered with power over Ethernet. This is a Cisco WAP 121 access point. Very good access point, although a bit dated these days. Let's just get a normal Ethernet cable. I've got all these random homemade ones, no actual normal ones. Let's use this orange one, it's nice and short. Okay, so let's plug it into this injector. This one here is an 18-volt injector. So you know, this on a power supply, which is this one here, this power supply is only 12 volts 2 amps. So it should match the settings we see on here. Yeah. Okay, 12 volts 0.5 amps, and it says PoE DC 48 volts. Okay, so will this get powered up using our 18-volt injector? Yeah, let's have a look. Okay, no. Again, because this device is expecting to meet the PoE standard, which means it's expecting to receive 48 volts from its injector. Otherwise it's not going to work. Okay, so these 18-volt injectors that you sometimes find are specifically for another type of device. Okay, so it can be a bit confusing sometimes when you're buying a PoE injector like this. Always make sure that if you're trying to meet the normal standard of PoE, you need a 48-volt one. These ones are for specific devices. Why do they exist? Well, before PoE became a standard, it was used by so I think Cisco might have been the first people to come up with it, and they were using a lower voltage before the industry said, oh, that's a good idea, let's do that, and then a standard is created. So there's, you know, these old adapters which don't follow the standard, but they still have a purpose. You know, somebody might still require something like that, but when you're purchasing one, just make sure you purchase the right sort. So let's have a look at this proper PoE standard injector. Plug in our access point, and straight away we're now getting power to our device. Okay, and let's try this onto one of our switches. And there we go, that's powered up, and it's also getting the Ethernet link from the same cable. Let's try that on the others. Okay, there we go. It took a bit longer to power on, but we saw that earlier, the Netgear just taking a while longer to carry out its negotiation. There we go. And there we go. So let's have a closer look at the difference between passive PoE or type. There's mode A or mode B, and mode A is active PoE and mode B is passive. Okay, so mode A is Endspan, or coming from a switch. Mode B is Midspan, or passive. So there's lots of names for them to get used to, but those are the two main types. So let's have a look at what is going on between these devices and the difference. If we just separate out a bit further here, I've just separated the different colours out here. Okay, so we've got orange, we've got the blue, we've got the green, and we've got the brown cables. Okay, I'm just splitting those out to see what happens on each bit of the copper. So let's just first of all test the green and the orange, which according to the pinout guide for mode A, green and orange, green is 1 and 2, orange is 3 and 6. Okay, so we can see according to that, that's DC positive and DC negative. Okay, and we can see that the fluctuations we get in the power are very much the same as what we saw. Okay, 2.4 volts, 3.5 volts. Okay, a little bit of a flicker going on, slightly different because we're now not getting the power from these other two. So for some reason, I'm not quite sure why, it gives you a little bit of few millivolts on those as well. Interesting. Let's have a look and see what the Netgear's behaviour is for that. Let's again test the green and the orange. Okay, similar to what we were seeing before, 1.5 volts there, 0.7. Let's have a look at this one. Probably a few millivolts on that, yeah. Okay, all slightly different, aren't they? Okay, but we never see this jump up to 50 volts, which is what you'd expect to be provided to an endpoint, and nothing on that one for this one, which is interesting. But we do get something on that, 1.3, 0.7, 0.6. Let's have a look at the Meraki. Hard to read those because they fluctuate so fast. Looks like 98 millivolts. No, it's fluctuating too quick for me to read. I'll have to slow the video down. Then we got very, very small, well, nothing actually really there. Okay, so let's have a look and see the same sort of thing on the injector. Okay, what's happening here? Orange, green. Just a tiny little bit of millivolt activity going on there, but nothing significant. And then we've got blue, brown. Oop. Help if I turned it on, wouldn't it? Ah, there we go. There's our 48 volts. What are we getting on these ones? Nothing. Just millivolts of nothingness. But there we're getting straight away 48 volts of steady. So that's coming through the blue and the brown. Okay. But why don't we get the same 48 volt PoE standard when we're testing on our switches? Well, the reason we don't is because it would be incredibly dangerous if this switch just punted out 48 volts like this does. And really, you wouldn't want to plug an Ethernet cable into here and plug it into your laptop, because your laptop doesn't need power. And what you're going to be doing is sending 48 volts into the laptop's motherboard. So it can be quite dangerous to use a passive injector if you use it in the wrong way. And the last thing you want to do is fry a piece of delicate networking equipment by just whacking 48 volts through it. 48 volts is not a hugely high amount of voltage, but it's certainly enough to damage electrical components or a motherboard. Now, a lot of motherboards and a lot of devices have protections built in, sure, but you can't really guarantee that. It's just not worth the risk. So therefore, you can't just plug into a PoE switch and just chuck out 48 volts through the data pair, through 1 and 2 and 3 and 6. Imagine if that just threw 48 volts down everywhere. Every single time somebody plugs something into a PoE switch, they'd be at risk. It could fry the motherboard, it could kill their network card. So you definitely don't want to be doing that. So how does the switch know to provide power to a device? How does it know that? How does that happen? Okay, it's done by a signal resistance. A resistance goes through the circuit, and it's a special key resistance which tells the switch that a PoE device is being plugged in and requires more power. And that signal resistance is 25 kiloohms, or it's actually between 19 and 26 kiloohms. But what happens is it sends out a small amount of voltage, which is undamaging, and the PSE knows what type of what amount of voltage it's sending out. So let's just say it sends out 1 volt. 1 volt, which is going to cause a non-damaging jolt to whatever's connected to it. If the return voltage is 1.0 25 kilo ohms less than the voltage it sent out, then it knows that it's detected a PoE device. Okay, I'll just show you how exactly that works. So what we're going to do is connect this cable here. Now this resistor here is 25 kilo ohms. Okay, so I've just turned this to resistance, and I'm just going to demonstrate that this is a 25 kilo ohm resistor. Okay, 25.1 kilo ohms. Okay, which will meet this. I think it's 19 to 26 is the signal resistance that it has to drop between. Okay, doesn't have to be exact. This is a good resistor for labbing because it's quite hefty. You can punt loads of voltage through it and it won't break. But typically in a circuit you're not going to find something this meaty. But this is good for our lab. Okay, so what we're going to do is we bridge. I'll do this without it connected. What we do is we bridge from our two pairs where we need the power. So what's happening now is the voltage gets sent out from the switch, goes around the circuit, detects that this resistance value is there, so it can measure the return voltage, and then it goes, there's a PoE device connected, so I'm going to send it more power. Now will that work? Let's find out. What voltage are we now reading on our circuit? Turn that to voltage. Okay, look at the difference here. We're now getting much higher readings, including 53 volts. Okay, so we can see on this particular switch we've got a flashing light here. Okay, this flashing light indicates that there's a PoE fault. Okay, this is because all we've done is put this resistor in place, and the switch is now confused about what's connected. It knows there's a PoE device because it's got that signal resistance, but the device isn't doing anything. It's just sitting there, not making any decision on where to draw current, what wattage it needs, what class it needs to fall into. There's a class selection going on as well when you plug a PoE device into a switch, and that's not happening. So there's a bit of confusion here, but we are getting power. We're getting 53 volts, we're getting 9 volts, we're getting 6 volts. We're getting all these different voltage values cycling around. Let's see the same thing happening on the neck here. Okay, 3 volts, 47 volts. Okay, so that will meet our PoE standard there. We're getting 24 volts, was that? A bit hard to read. Again, it's flying through the process quite quickly. Let's go even to the next one. See that flicked through? That was quite easier to read there. It went 2, 9, 47.5. Okay, so we can see we're getting now much higher voltages coming through, all caused by the magic of this 25 kilo ohm resistor. It's now telling the switch to give us more power. It's a very clever little layer 1 handshake going on here to do this. Have a look at this one. Don't know if you could see that. Might have been some reflection on the screen. Sorry about that. So on the Meraki we're getting, let's put that there. .55 volts there. So they all behave slightly different, but we can now see the voltage values are much higher that we're getting by just connecting this. Now of course you don't have to use a lab resistor like this, which is a bit chunky. We might have some other ones here. Let's have a look. Just measure the resistance on these quickly. So we've got just some of the, for different labs and things, I've coupled these together. 6.6 there. .216 kilo ohms. That's not going to help us. 50 kilo ohms. So that one's 14. What was that one? 14 and 6. Let's just add those together. .9. So that should meet the standard as well. Let's see if that one works. So we need to bridge across green and orange with this resistor. Let's just do that with some crocodile clips. Put that into the switch. And yeah, I can see the lights come on. So that should be doing the same thing, giving us that fluctuating voltage. Oh. There you go, 53 volts, 8 volts, 26 volts, yeah. Hopefully you can read that. So you can see that's doing the same thing. So different resistors doing the same thing, and I've just thrown that together. Again, I'm just making sure I'm falling into the signal resistance. So incredible bit of technology going on here to make sure that the switch can safely carry out a very quick negotiation to make sure that it only provides that 50 volts, that 9 volts, or the increased voltage to power something like this when the device has told it to do so using that key resistance. So that means that every single PoE device out there has got a resistor in it of 19 to 25 or 26 volts, so including this. So this is a PoE device. Just get rid of some of this quickly. Might need those later, but just put those back here. So this must be a PoE device of some description, because it's taking power from the switch and saying, yes, I'm a PoE switch. So that must carry out that negotiation. So therefore it must have a 25 kilo ohm resistor in it. Yeah? This must have a 25 kilo ohm resistor in it. So I don't know, let's put this to the test. Let's have a look. Let's open this bad boy up. Okay. What do we think? Let's replace these with some needle probes. Put this to resistance. Just check that was working. Yep. Okay, so let's see if we can find our 25 kilo ohm resistor in here. No. Ah, look at that. So between these 2 points, you can see I'm getting a reading of 24.8 kilo ohms. See what I get on these two. 24.8 kilo ohms. So I get to, there's 2 on this one. I don't know why there's 2, but without reading a schematic of how this works. But you can see this point here, between these 2 points here, I'm getting a reading of 24.8 kilo ohms. That meets the signature resistance. So there we go, we found our signal resistor to tell the switch that it's a PoE device. Where did I put that screw? Anyone see where I put the screw? Ah, there it is. Right, let's just put that back on. Okay, so we should have the same resistor in, let's say, this device here. So should we open this up? We've got a hammer somewhere. Let's just give it a good bash with this. So I don't know how, again, I don't know how the circuit, you can't find a version of the wiring schematic for this on the internet. So it's quite complicated, far more complicated than this. This is just a basic device to test the PoE, but this is doing a whole lot more. There's a whole bunch of stuff in here. I don't know what any of this stuff does, but I do know that one of these things must be a 25 kilo ohm resistor. Yeah, it has to be, otherwise this would never work. So let's find it, okay? There's a whole bunch of different resistors in here, so you know, all I've done is I've gone around checking the values of these resistors. I can see there's a 91 ohm resistor there. In fact, it's 5.4 ohms, which wrong. Yeah, no, that is wrong. That's a different one. I'm sure it's one of these. 65 kilo ohms. Normally it's the ones that are called R, you see, that's what I'm looking at. I think that they are 50 ohms. Can you see it? There's R90, that might be it. Let's have a look at that. 53 kilo ohms. No, we didn't. Somewhere in there. There it is. R91. So it's this one here. R91, if you just have a look, we'll just do that again. So I'm just going to put that end on there. That end on there. 24.7 kilo ohms resistance reading. Okay, as you can see. 24.9 kilo ohms. Okay, so that's the signal resistor. Power goes in, goes through that resistor, and that tells the switch this is a PoE device, and it knows to then give it more voltage. So then it bumps up the voltage, and then this goes through the second stage of the PoE detection, if you like, which is the classification. It chooses a class. So there's 4 classes, and each one needs a different amount of power, a different amount of wattage that it takes. So that really is how PoE works, and that can give us our building blocks now for maybe designing a PoE device. So it's interesting what we were seeing earlier on this one. I did put some cables together. I put these funny cables together just to see what would happen. This has just got the green and the orange connected. So if I just put the green and the orange connected into here, it should still think it's a device. Yeah, it still knows that's a switch. But if I go into here, it shouldn't detect it, yeah, because we know that the power's coming in on the blue, the blue and the brown. So I've got another cable I made with just the blue and the brown. It's on here. And this should give us our midspan light. Okay, but we won't get anything from here. So just reiterating what we already knew, that it's coming through on 2 different pairs for PoE passive or type B, and active or type A, or midspan or endspan. Okay. And it's funny that we get this fault light as well on this switch, which we don't see on the others. So when we apply our signal voltage, sorry, I use the other one, not that one. When I apply the signal resistance, it's always better to do this before plugging in, because then you're not accidentally sending 50 volts onto your fingertips. 50 volts is considered safe. You know, you shouldn't get an electric shock from it unless you stick it in your mouth or something silly like that. But It's always best to just err on the side of caution when you're doing things like this, so you just don't accidentally do something silly. So you can see on here we're getting this flashing light, which according to the switch is a PoE fault. Okay, so it's detected something, but there's some sort of fault. Now, I don't get that on any of the others, I don't think. On this one here, I get no light. Oh, I get a little flicker. Okay, so I do get the similar kind of thing. Yeah, it says there yellow is a PoE fault, but you can see it just gives me a flash. Every now and again I just get a flash. On this one, oh, there we go. There's the light over here. I'm just getting PoE alive, a flash on it. I don't know if you can see that. There we go. See the flash there? Just about. Okay, and let's see if we get anything on the Meraki. I see no lights on that at all. So different behaviours again, depending on what we get here. Anyway, that's really it. I think it's very interesting how the layer 1 negotiation works. It's a very nifty little way of safely making that PoE negotiation and then sending power to the device. And like I say, that gives us our starting point for building a PoE circuit. And we've learned about the difference between passive PoE and active PoE and the different names, and we know that the voltage that's to be expected is 48 volts. So hopefully that's all been very interesting. I've certainly enjoyed this little project, and thank you very much for watching.